Hi, welcome to the analysis, design, and simulation of a flyback. Now, why use a flyback? What would be the applications? Well, the applications would be anything from small, low power electronics all the way to powering a television set. As a matter of fact, most television sets in the old days, the ones with the CRT, had a flyback that would generate voltages up to 25,000 volts. Well, why? What are the advantages? Well, here's just some of the advantages. The first one is that they're simple to design. There's really not too much calculations involved with them. There's no output inductor. For example, if you were to design a forward converter, you would have to design the transformer itself, but then you also need an output inductor. Another reason I use a flyback is low parts count. Basically, you just need a transformer, which is the flyback, a MOSFET, a diode, a capacitor in your load, and basically a PWM. With flybacks, you can also wind multiple secondaries, so you can have multiple outputs. Now, some of the disadvantages are that they're usually reserved for lower power. If you're using a P1811 core, you can get about 20 watts, but typically you want to use flybacks for anything below 100 watts. Okay. Now, another disadvantage is that your output load, you have to have an output load. Otherwise, if you don't have an output load, the output diode starts peak detecting, and what happens is that your voltage starts climbing, and you overvoltage the output filter caps. So you never want to operate a flyback with auto load. Otherwise, you're gonna damage your capacitors. So that's one of the disadvantages. Now, before we continue with the flyback analysis, you're going to have a little bit of background information. You need to know that flybacks use a scheme where you use pulse width modulation, or for that matter of fact, most converters use PWM. PWM is really pulse width modulation. Now, one can ask, well, how does the PWM is used to control voltage? Well, a PWM, basically you modulate the turn on voltage, or the time that it's on. Okay, so typically you would have a waveform that looks like this, a square wave, and the frequency will stay the same, which means that the time from here to here, the period, will stay the same, but this time on from here to here varies. Okay, now when you vary that, you vary the average voltage. Now, if you were to put this square wave and you filter it, put a filter, okay, whether it be an inductor and a capacitor, the output at the filter will be a voltage that is average. Now, you can take the average, this waveform, and average it, and you can put it into this equation, right? So basically, when you average this waveform, which is the blue, okay, it's going to be the mathematical formula is 1 divided by the time period times the integral from 0 to Tp. In other words, from T0, or 0 times 0, all the way to Tp. Now, if you see here, you have two sections. You have this section, and you have this other section. Okay, so that means that this would be the first, So this would be the first integral. Okay. And during that integral, the voltage will peak to a certain peak voltage, which is right there. Okay. So that peak voltage is defined within this equation times dt plus 1 divided by the time period of the second. So this would be the second. Now in this case, the voltage right there is 0 volts. So that goes there. There goes 0 volts right there. Okay. So what does it mean? Well, basically, in reality, when you do this mathematical equation, all you're really doing is you're finding the area of that, and hopefully find the area of the second. But since it's 0, basically that goes to 0. This area is that area, and this area is that, which is 0. So when we're talking about area, what you want to do is you want to get the width of this area, and that area is T on minus 0, which is noted there. And then the height is the height from 0 volts to V peak, which is that there. Okay, and you divide that by the period, and you get that equation, which is really the V average is equal to T on times V peak divided by TP. Now this section here, T on over TP, is also known as D, or in this case it's the duty cycle. Okay, so if you have a waveform, right, if you have a waveform and you want to calculate the average voltage, as long as you know what the duty cycle and V peak, you can calculate the average. Okay, so basically that's what pulse width modulation. So let's define duty cycle a little bit more closely. Again, we're using a square wave. Okay, and square wave has two intervals. It has the time on interval, and typically when we say time on, this is the time that the MOSFET is on. Okay, and then there's a time period, another second interval defined as T off, and that's when the MOSFET is off. Okay, now the time period where it's on is from D Tp, in other words the duty cycle times the time period, to T0, which is 0 volts or 0 time, and T off is defined from Tp to D times Tp. So here's the definition. So Tp is really the time period, which is the reciprocal of frequency, basically from here to there. That's your time period. Okay, and as I mentioned before, time on is the time that the MOSFET is on, and that's D times Tp. T off is the time that the MOSFET is off, and like I mentioned before is Tp minus this, which is D Tp, and when you factor the Tp, you end up with 1 minus D times Tp, and it's also known as D prime. Okay, so now we have D. We officially defined it. D is the duty cycle, and it's really a relation, and it's really the relation of T on divided by Tp, which is the time that the MOSFET is on divided by the time period. Okay, so how do we analyze a flyback? Okay, well, here's a very simplified schematic of a flyback. If you see, you really have a input voltage. Right here I have a little terminal, but I can go ahead and, let's say, put a voltage source. Here, connect it and just name this Vn. Okay, and let me put the plus negative here, and we're going to have a transformer. The primary will say that it has primary turn of 1, and we'll say the secondary has n turns. Now the other thing that you want in property of a flyback is you see that the dots are out of phase with each other. So that's that little note right here that I have, that the transformer is out of phase. And then you're going to have a switch. The switch is implemented with either bipolar transistor, or you can implement it with a MOSFET. And typically we use a MOSFET. Okay. Now the other component that you need is a diode to rectify the voltage and open when needed, and a capacitor to store the charge, and you have an Rload. Now you need one thing that I want to make a note is that a flyback is a coupled inductor and it's not a true base transformer converter, like for instance like the forward converter. A forward converter does not store energy. Basically, when you turn the MOSFET on, the energy is not stored and it's transferred directly to the secondary. Now a flyback does store energy. So basically you have, during phase 1, energy is stored in the flyback during the T-on period. And now remember, T-on is the time when the MOSFET is switched on. Okay. Then once during that time, energy is being stored in the transformer. Okay. Now when the switch opens up, then the energy, in other words the magnetic flux that has built in, that energy then is released. It's released by turning on the diode, and the energy that is stored in the transformer is used to charge the capacitor and power your load. And that is done during the T-off. Okay, so how do you analyze a flyback? Well, typically to analyze, you need to do is draw the schematic for when the transformer is in the T-on period. Once you draw the schematic, you can write equations. Okay. Then you have to draw a schematic for the T-off interval. Once you have that schematic, then you can write equations for the T-off. So how do you do that? Well, let's draw the little schematic. So here's the schematic of the transformer during the time that it's on. And when they say that it's on or T-on, what I mean is that the MOSFET switch is closed. So right here you can tell that it's closed. Okay, so what happens when it's closed? Well, since this is positive voltage, that means there's a positive voltage on the plus sign. Okay, and if you have a positive voltage on the plus sign on the secondary, you're going to have a positive as well. Okay, since the non-dotted on the primary is connected to the ground, you have a negative. Okay, so that means you're going to have a negative on the secondary undotted side. Okay, now remember there's a diode here. Okay, so if this negative is going to the anode, it turns off the diode. So basically you have a diode that's off, so you can model it as an open. Okay, so during this time at steady state, okay, the load or the voltage that the load C is provided by this capacitor. Okay, so basically this capacitor is providing the voltage to the R inductor. During this time, okay, the energy is being stored in the inductor or the primary inductor. Okay, now once we have this schematic, now it's very easy to write the equations. So just by inspection, you know that the voltage of the primary, which is Lp, is going to be actually Vn minus 0. So basically this voltage will be Vn. Okay, and the time period, we define it as dTp. Okay, so now we look over at the off time. Okay, during the off time, the MOSFET is open, so it's left open. Okay, so the energy has already been stored, and since it tries to keep the same current flowing, the signs or the polarity flip. Let me go ahead and change that color. So basically the non-dotted on the primary becomes plus, and this becomes negative, and the dotted, since the dotted on the primary became negative, this is negative and this is positive. Okay, so remember we had a diode here, so now we have a positive going on the diode on the anode side, so that diode is on, and that can be modeled as a short. So during this time, then the energy that is in the secondary, or actually in the stored in the flyback, is used to charge the capacitor, and it's also used to charge the load resistor. Okay, so in this case, you can see that as the inductor is discharging, or actually is charging the capacitor in the Rload, you can see that if you look at the voltage that is reflected back toward the primary, since you have a positive here and a negative, that means you're going to have a positive and a negative here, meaning that you're going to have, let me change this color, means that you're going to have a reflected voltage back to the primary, which is going to be V out divided by N. Okay, now during this time, made a little error here, should be time off. Okay, time off, and this time period is 1 minus D times Tp, the time period. Okay, so now we have an equation for the primary inductance. Now we can calculate, or we can see that that the current of the primary can also be calculated. Okay. Now, in this case, since the current is dependent on this voltage, and you're going to have a current that actually ramps up like this, okay, during the time on, and then when it turns off, that current should go down to 0 until the next cycle. So during this time it's T on, and this is T off. So during that cycle, the slope is actually V divided by L. Okay, so we can write an equation that says that the current of the primary is actually Vn divided by L times T on. Okay, now if you look in the off cycle, if you notice, the switch is open, so there's no current in here. So now we can say that during the off period, the current going through the primary is 0. Okay, so now we now have equations that can describe both the current and the voltage of the primary of the flyback. Okay, so now with that being said, now we can draw a little diagram, and here's the diagram showing the voltage across the primary and also the current of the primary. And during this time, when it's on, we know that this is Vn. Okay, and when it turns off, the voltage across the primary is negative V out divided by N. Okay, now for the current, like I said before, this slope is Vn divided by L, and then during this time there's no current. Okay, and this peak, how high it changes, that is expressed by Vn divided by L times T on. Okay, so now you have two waveforms and you have a set of equations. Now what we can do, we can apply the volt-second rule to derive a transfer function. Okay, so what is the volt-second rule? Well, the volt-second rule basically says that the average voltage across an inductor at steady state must be 0. So with that being said, we use this waveform. Okay, we know that during the on time, the voltage across the inductor is going to be Vn, and the time is T on, and during the time off, the voltage is V out negative divided by N. So we have these two equations. So this is during the T on time. We know that T on times V, and the voltage across the primary is really Vn times the duty cycle times the time period. Okay, and during the T off, the voltage across the inductor times the duration of T off is really negative V out divided by N times 1 minus D times Tp. So these two equations we set these two equations in here. So basically this is, let me change this. So basically this is, nope, wrong color. Okay. There. Really. So this is T on. This is T off. Okay. So basically T on minus T off is equal to 0. So this is the volt-second rule. Volt-second rule. So basically we're summing them and they all have to sum up to 0. So all we have to do is solve for V out. Okay. So here's the equation, brought it over. So it's V out divided by N times 1 minus D, close parenthesis, Tp equals Vn times D times Tp. So you end up with this equation. Okay. So this is the transfer function. It's the transfer function of a flyback. Basically it tells you that what the output voltage will be, and that and is dependent on the duty cycle and the input voltage. Okay. So let's do a design example to help solidify some of the concepts. Vn. Let's hear some of the specification. In this example, I'm letting Vn be anywhere from 24 volts minimum. That would be the minimum. To a maximum of 34. And we want to regulate at 12 volts and have a current capability of half an amp. And we will use a frequency of 100 kilohertz. Okay. Now these are my assumptions. I'm going to use a duty cycle of 0.5, and the second assumption that I will be using is that it will be 100% efficient. Now remember this is just an assumption. It's not a real world, but it's okay for simulation. Okay. Because since we're using a simulator, I can use ideal parts and I can come up theoretically and get 100% efficiency. Okay. Now please note that there is a design equation that are in most of the books. In that design equation, you basically are trying to calculate the inductance of the flyback that will give you the power output that you need. But we're not using that. What we're going to do is we're going to calculate the voltage, we're going to calculate the currents at the secondary, and then we're going to transfer them to the primary and then use the information to calculate the primary inductance of the flyback. Okay. So here's the steps. The first step that I use is calculate the output power. Okay. In this case, we have power out, or PO. That's 12 volts times the output current, which is half an amp. You end up with 6 watts. Okay. Now we're going to assume that we're going to have an efficiency of 100%. And the reason I'm using this of 100% is to simplify it. Okay. So assuming that efficiency is going to be 100%, if the output is 6 watts, then we're going to say that the input is also going to be 6 watts. So basically, power in is equal to power out, and that's going to be 6 watts. Okay. Second, we calculate the average input voltage. Okay. So to calculate the average input voltage, okay, which is IN average, it's power in, and you divide that by V in minimum. So using our design example, power in is 6 watts and we divide it by 24 watts, so we should have a quarter of an amp of average current. Okay, now recall that this average current is being supplied by this power supply. Okay, now this input current is going in, and it's an average current. Okay, now recall that from the analysis that we did up there, we know that the current of the primary inductor actually looks like a sawtooth, or this sawtooth looking waveform. It wraps up and then turns off, and then remains off for T off, and then wraps up again. Okay, so you already have a relationship that this I peak, okay, and you also have a relationship where you have this input average current. Okay, so if you have this waveform, you can actually calculate the I peak, or the peak current of the primary of the transformer. So to calculate or develop a relationship between I in average and I peak, you can integrate or average the sawtooth of the peak current. So basically, I in average is 1 divided by the time period times the integral of the current during this time, okay, which basically means that you're looking for the area. Okay, now keep in mind this is a triangle, and if we make an assumption or just say or think that, okay, if we go up here and make it a square wave instead of a triangle, okay, we know how to calculate the area of square. But since it's a triangle, we know that a triangle has half the area of a square, so we use that 0.5 to adjust for the area. Okay, so we know that to get the average is 0.5 times the peak, which is this height, times the width, which is dTp, which is this width. Okay, and all of that is supposed to be divided by Tp. Well, the Tp's cancel. Okay, and so you end up with I in average equals 0.5 times D times I peak. Okay, now we assume that D is going to be 0.5. Okay, so from this equation we get this second equation, and finally we get this relationship where if we know what our average voltage input is, current, all we need to do is multiply times 4 and we can calculate the peak current. So therefore, if we have an average current of a quarter of an amp, we know that the peak, assuming that D is at 0.5, we know that the I peak will be 1 amp. Okay, now with that information, now we can calculate the primary inductance, and we use this formula, which we all know, which is V is equal to L times di dt. We solve for L. Okay, so in solving for L, we're actually solving for the primary inductance, and that is V divided by di dt, which is really the voltage in minimum divided by I peak times T on. Okay, so T on is defined as, or actually the time can also be defined as D divided by frequency. So in this case, we know we set D to be 0.5, so we divide it by 100 kilohertz, we end up with a T on of 5 microseconds. Once we have that, we plug in the numbers. We got 24 volts, 5 microseconds, 1 amp. So we should come up with 120 microhenries for the inductance of the primary of the flyback. Okay, and then the last is we need to calculate the turns ratio. Now, to calculate the turns ratio of the flyback, then we have NR, which is the turns ratio, is really the turns of the secondary divided by the turns of the primary. We can set this to be 1, okay? But we also know that V out is equal to the turns ratio times Vn, okay? So we have this equation then. We know that Vn, V secondary, or the turns ratio, is really V out divided by Vn. So in our case, okay, we know that V out is going to be 12 volts, okay, and Vn is 24 volts. So we have a turns ratio which is 0.5. Okay, so now we have enough information where we can simulate it. So in the next video, I'll run a SPICE simulation and see how the calculations or the voltages and currents that we calculated, whether they agree with SPICE or not.